Yes, my little tripod gave up. Okay, let me make sure. Any questions from stuff? I mean, the last time I saw you, we had just taken a test, so I don't think anyone's done possibly any more homework, although you should be working on 5.4 already. I could have made that do, but like I said, I was trying to be nice, feeling that I don't like it, feels icky, but you are totally ready to do 5.4. So just to kind of review, if nobody has any specific questions, let's remember what the heck we've done so far. Can somebody remind me what these are?
Difference identities or?
Good, what are they? Yes, what are they?
Sine
Yes.
A, cosine.
Yes, sine A, cosine B, plus sine B, cosine A, right? The sine's a nice guy. Let's say terms, let's leave it a plus. This would be nice to everybody. What's cosine of A plus B?
Me first, me first.
Cosine A, cosine B,
Minus sine
minus sine A. So, that entire thing, remember that thing I did where I had weird ass things happening and blah, 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 blah. Remember the alpha and the beta above? Right. That whole thing was to show you, even if you didn't understand every step, was to show you that these come from definitive physical truths. They're not just shit we sort of were like, that sounds good. They're just what would happen if I actually analyze it. So you don't have to know how to do that whole derivation. You do have to memorize these, and hopefully you did, because otherwise you probably sucked on that part of the test. Okay. You guys all with me? All right, now, just to show this off for you. There's a sum and difference for tangent. And by the way, let me do this. If this was minus, how would this change? If this was minus, how would this change? Yeah. It's the first time we've ever seen plus minus and minus plus are actually different. You normally say give or take, plus or minus, but now it's minus plus that has meaning. That plus goes with that minus goes with that plus. Kick ass. I like it. Now, what I'm about to show off is the fact that I do not have the tangent one memorized, because I don't want to. So you don't have to either. Do they give it to you? I think they do. Here we go. I don't even know why I'm writing this up here, but just to do it. All right, that's exciting. So if I ask you a question on a test or a quiz that involves this, I would give this to you. You guys all with me? So there's two levels of this, to be honest. As a department, we've decided what identities you should memorize as a student and which ones you don't need to. So I could make you memorize more than we decided on. But what's nice for me is everything we decided wasn't important or stuff that I don't have memorized either. So these two I know. This one I have no motivation to memorize it, because what I normally do is if I want to know what tangent A plus B is, I can do sine A plus B, cosine A plus B, and then just divide the two. Because that's what tangent is. It's sine divided by cosine. Is that cool?
Yeah.
Okay. All right. Maybe. So let's do this. Can you guys take a minute and figure out what the tangent of 75 degrees is? Doing it this way. First step is to do what with 75 degrees?
Break it up into two numbers.
Yeah, I don't want to do 60 plus 15 because I don't know anything about 15. So how would I break 75 up?
45, 30, 40,
30, 45, 45. You guys should have seen this in the homework already. You'll see certain angles over and over again because there's only so many angles we know. There's only so many ways to put them together, right? Okay, so try it. Go ahead and throw all that stuff together. See what happens. What's it look like way over here? Can you see that? So the first step is just plug and chug, right? If you want to, if it helps you, you can say, okay, this is A, this is B. But all you're really doing is plugging this guy into wherever A is and this guy into wherever B is. So let's see, I get tangent of 45 plus tangent of 30 divided by 1 minus tangent 45 tangent 30. Now some of you guys might be worried if you change the order. Hopefully you can see if I change the order, it doesn't matter. Okay. You get the same number, you have to. Okay. How far can we make it here? What's tangent of 45?
1.
Kick ass. What's tangent of 30?
Rad 3 over 3.
Kick ass. Tangent of 45 is still 1, tangent 30 is still rad 3 over 3. So this is where weirdness can happen. This is why I wanted to focus on this. So pretty cool with what's happened so far up here. It's just a bunch of plug and chug, right? Okay. Why is that not acceptable? Unacceptable? Why is that not acceptable?
Wait, hold on. Is it 1 minus tangent 45?
Times tangent 30. Yeah.
Oh,
Wouldn't that just become negative 1?
So you, sorry? No, definitely not, because the top and bottom are not the same number, different signs.
it's simplified.
Like if it was 1 plus 4 over 1 minus 4, that's 5 over negative 3.
Multiply by a conjugate?
Hey, all right, now we're talking. So let me write this again. So the major problem with this is that there's a radical on the bottom. So how do I deal with that? Well, if it was only this, I could multiply by rad 3, and then I could kill the radical, right? But it isn't. It's got more shit. So I don't know if you guys know this. I just heard the right word from over here. There's something called a conjugate. And the only other place you normally hear that word is when you conjugate verbs in a different language. Je vais. All right, sorry. So the conjugate in mathematics is same numbers on the bottom, opposite sign. So why do we do that? Yeah, the middle terms cancel on the bottom, which is the only place a radical could have still been left alive. So we've killed all the radicals, right? We're good tyrants. Get the radical element and kill them. So on the bottom you're going to get 1, middle terms cancel, minus, what's rad 3 times rad 3?
3.
Yeah, half of 3 times the other half of 3 is a whole 3, and 3 times 3 is crazily enough.
Or 1/3.
Beautiful. On the top, I'm going to get a lot of shit because nothing cancels. You get 1 plus rad 3 over 3 plus rad 3 over 3, so plus 2 rad 3 over 3. And then what's rad 3 over 3 times rad 3 over 3? Well, we know exactly what it is. It's freaking 3 ninths. So I get 1 plus 1/3 is 4/3 plus 2 rad 3 over 3. 1 minus 1/3 is 2/3. What can I multiply top and bottom by to kill all my internal fractions? 3. So I end up with 4 plus 2 rad 3 over 2, which is 2 plus rad 3. Crazy shit. Let's check this. Anybody have a calculator? Does no one have a calculator? Anybody? You know, like, if we just wait long enough, you'll do it, Jeff. No, get your calculator if you got one. What was the original problem? What is it we're trying to figure out?
Tangent 45.
Tangent is 75 degrees, so figure out what is the tangent of 75. Make sure you're in degrees. So what do you get?
3.73.
Yeah, so it's roughly 3.732, blah, blah, blah. Now, do 2 plus square root of 3. Good, that's how you check this shit, right? I'm gonna want exact answers from you because I'm an asshole. So I'm gonna want this. How do you check yourself when you do this and you do that and you see that they're the same? Because that's your claim after you're at the end. You're saying that this is this. Does that make sense? Yes.
So, on the calculator, you gotta make sure it's in.
Degrees in this case, to do this, because this is degrees, yeah.
Gotcha.
So that's gonna be an ongoing struggle, is to remember to check the mode you're in. And I have lived through the experience of having mine in the wrong mode, and I got a wonderful F on a quiz. It was great, so learn from Jeff. He's first learning this shit. Anyway, sorry. I'm not bitter still.
You sure about that?
Yes, I am. Okay, so this is all stuff we did before. This was a little new, but it's nothing you have to memorize. It's just going to be a plug and chug thing for you. You can look at the formula that's in the book. Is everybody with me? Today I'm going to give you a sheet of all the identities you're supposed to know, and all the other ones you're not supposed to know. You're not supposed to memorize. Nothing forbidden about the other ones. Okay. Any questions on that? I really want you to understand the formula we used, this guy, you don't have to memorize it. So when you're doing homework and you get a question like this, you can just look up the formula, not a big deal. Okay. You can do that with everything when you're doing homework, so who cares? Yes?
Would it have been wrong to multiply by 1 minus rad 3 over 3 instead of 1 plus rad 3?
It would have, because the bottom would have still had a radical. Yeah. The reason the bottom doesn't have a radical is because you've set it up so the middle terms cancel. Yeah. Okay, I'm gonna erase all this. Good? Yeah. Okay. All right, so now what I want to do, I think I already did this before, but just to make it formal. So very quickly, remind me what sine of a plus b is. Yeah, sine a cosine b plus sine b cosine a. So sine's a nice guy, it takes turns. So what is sine of 2 theta, which is also known as sine of theta plus theta? We've done this already, but just to remind you guys. Sine of 2 theta is just sine of theta plus theta. And I know what to do with any two angles when I'm adding them inside of sine. It would be sine theta, cosine theta, plus sine theta. So when they switch, they get, it's kind of silly. It's like I have exactly the same two toys, and I'm like, let me switch with you. Same toy. It's like, all right. So what is that, of course? What's sine theta cosine theta plus sine theta cosine theta? 2 sine theta cosine theta. So that's what sine of 2 theta is. Now, I might want to move up to the projector because I don't think I have any good pens. All right, no. Now, take a minute. Try to do cosine 2 theta. Well, I set things up here. Let's see. Figure out what cosine of 2 theta is. same exact way. Using the correct identity, of course. Is this room? Alright, I'm gonna mess with the lights for a second just to see if this room does this correctly. No. Holy sh! Oh, hey! Alright, so happy. Doesn't take much to make me happy. Just this front light makes it hard to see what's going on. Oh, let me do this. So help me out. Cosine 2 theta is going to come off of cosine of A plus B. So what is cosine of A plus B? Cosine A, cosine B, sine B. Okay. So cosine 2 theta is cosine of theta plus theta, which is cosine theta, minus
Sine theta, sine theta.
sine theta, sine theta, which is also known as. Now, here's what's really exciting for you guys. Remember cosine's an asshole? Remember that?
Yeah.
Here's another place where cosine's an asshole. Sine of 2 theta, there's only one possible thing. It's 2 sine theta cosine theta. Cosine of 2 theta, there's 3 things it could be. So you're like, I only see one thing, Jeff. But remember, if I see squares on my trig stuff, that relates to the Pythagorean identities, correct? So watch this. Cosine squared is 1 minus sine squared. Is that cool? So isn't this 1 minus sine squared, 1 minus 2 sine squared? Because cosine squared is 1 minus sine squared, and I have another minus sine squared. Is that cool? I could also do, start over again. Sine squared is 1 minus cosine squared. So then I get minus 1 minus negative, so plus, so I get 2 cosine squared theta. So cosine 2 theta is either cosine squared minus sine squared, or it is 1 minus 2 sine squared, or it is 2 cosine squared minus 1. And there are problems where one of these is the right way to go, or a couple of them are good, or, right? So that's cosine main. And look, cosine's an asshole here too. Me first, you go second sine. And so there's, the idea of cosine being an asshole, I love it because it just kind of carries through almost everything. There's one place it doesn't quite work, which is too bad, but it almost works perfectly. You guys semi-okay with what just happened?
Could you go up a little bit?
Yeah. Which part, sorry?
Just for second
Just,
cosine.
So just to remind you guys, all we did was we plugged theta in for A and B. So that immediately led to this. And then we replaced cosine squared with 1 minus sine squared, which makes it 1 minus 2 sine squared. And then we said, we can replace sine squared with 1 minus cosine squared, which leads to this. So there are 3 ways to represent cosine 2 theta. Okay, I like that. That's the appropriate reaction. It's sort of like this. Perfect. So we sort of saw examples of what this is going to do for us. You're going to have to verify identities. So if I see, real quick, let me see if I can find one real quick here. I probably can. You see, I'm so confident, Jeff. I know. There's a perfect one. Oh yeah, that's gross. You don't want to do that one? I think that's homework. I'll leave that one for you. Sorry. Yeah, this one. So everybody got this stuff?
Yeah.
You guys good? Somebody still writing?
Oh,
You're good, you're good. Keep going. Okay. So let's try a problem out. Yeah, I'll keep this up here. So this says verify the identity. Let me remind you guys. When I'm trying to solve an equation that is different, if I was trying to solve the equation x plus 1 equals 7, right? X plus 1 equals 7, what would I do? I know this is deep. X plus 1 equals 7. Subtract 1 from both sides. Here's what students forget. Why am I allowed to do that?
Because you assume it's equal.
Because of the equality, not because I said so. That's never the right answer. Because it's a property of equality. If I have two things that are equal to each other, and the stupid thing we always go to is a balance. If I have a balance that's perfectly balanced, and I take something from one side, I have to take it away from the other side to keep the balance. So if I know two things are equal, and I do the same thing to both things, the equality holds. This problem says verify this is true. I do not know if it's true. I am not allowed to do stuff to both sides. I have to take one side and work with it. I can maybe take the other side and work with it. You guys with me? So the minute if I subtract one from both sides, I'm wrong. I can't do that. I don't know if this is true or not. So does anyone see something I can immediately do based on what we just talked about? We just talked about.
Cosine 2x.
Say again, sorry.
Cosine x squared.
I don't see any squares yet. I don't see any trig functions that are squared. Do you see that? I see a sine x and a cosine x. I haven't squared anything yet. Huh?
Is that sine squared x or sine 2x?
That's, what do you guys think?
Sine 2x.
Yeah, that two's big. Yeah. So please, dear God, I know I write really, really bad, but I try to do good here. So that's sine 2x, yes?
Make it cosine squared x minus sine squared x.
No. That's cosine 2x. So what's sine 2x?
2 sine x cosine.
2 sine x,
Cosine.
cosine x. Is there anything else I could really do here? I'll answer it for you. No. There's nothing really substantive I can do. So let's go to this side. What's the immediate kind of algebraic thing I can do?
Foil.
Foil. Go for it. I'll wait. Be really careful. The answer is not sine squared x plus cosine squared x. You lost your middle term if you do that, right? So take a minute, foil that sucker out. Maybe write it twice if you need to. Right? Foil that sucker. Be careful. I need to go back on my head so you can see that. Switch the S and F. So just in case you're having some trouble, something squared means it times itself. So what do I get?
Sine squared x plus 2 sine x.
Yeah,
2
sine squared x plus cosine sine x plus cosine sine. So I get plus 2 sine x cosine x
Plus cosine squared.
plus cosine squared x. And what do you see in here?
Pythagorean idea.
In fact, real quick, even if you didn't see that, do you see how I got 2 sine x cosine x?
Yes.
Which tells me for this to be true, everything else has to become, and do they?
Yes.
Now, is it good to stop there and turn this in?
Yeah.
Just, you
Draw
gotta
the line and check.
There we go. And I don't know if you guys understand, but that communicates to me that you understand what the hell you just did. So as the person grading your work, I cannot read your mind. I really don't want to be honest. So what I need from you is some indication that you understand what you just did. Yeah.
So I was able to follow along with what we did, but I am confused how we went from sine 2x to 2 sine x cosine x?
So that is what we just focused on. Where did I put it now? Oh yeah, I put it up on the board. Yeah. Yep, good. So we know that. So what's sine of 2d? Sine 2d.
Cosine.
2 sine d cosine d. Right? Is that cool?
It is basically another identity almost.
And one more identity, exactly.
Okay, that makes more sense.
One more identity in a giant pile of identities. Okay.
Is that true for the right side and cosine as well?
No.
Is it just sine?
Cosine is this guy. These three options here. right? And again, this is just a consequence of the fact that cosine of a plus b is this. So when I make the angles the same, I that's what I get. Okay, maybe. So this is fundamentally what math is. We identify a relationship. And then we're like, well, what if this? So then we try it, and that relationship leads to other relationships. So we verify this is true. That was that craziness with the giant triangles and blah, blah, blah. Therefore, I can investigate stuff that relies on adding angles together, because now I know how they act. So that's why I can verify what cosine of 2 theta, because that's just theta plus theta. I can use my addition formula for cosine that we verify. So you can look at this as different from this, but they're really the same thing. Not sure if you guys are really interested. This is this, if I make the angles the same inside. They really are the same thing. In terms of memorization, you can go ahead and memorize these if you want to.
So those three right there are what you wrote up there.
No, so this leads to these,
Those three.
Yeah.
Gotcha. Okay.
which is why I said this really is the same as this. Okay. So, let me remind you something we know. Let's look at cosine of 2 theta. So we know that, for example, that is 1, let's do this way first. That is 2 cosine squared theta minus 1. Let's look at this first. So let me see if you guys are really with me on this. This is going to be silly, but just go with me. If I put cosine 22 degrees, how would I write this side? You can do it.
11 plus 11.
Huh?
Cosine 11 plus 11. So it would be
No, don't overthink it. If that's 22 degrees, can somebody tell me what theta is?
11.
Good. So how do I write this side?
2 cosine squared 11 minus 1.
With the little degrees on there, right? Okay. You guys understand? So what does that mean? Whatever angle this is, this angle has to be half of it. And we see that. This is 2 theta, correct? So what's this got to be? This has got to be half of that. This has got to just be theta. Let me stop for a minute. So what if I wrote, so what is cosine of theta then using this formula?
Cosine squared theta minus 1.
No. Sorry, no. Thanks for playing. What does this formula say?
Minus 1.
What does this formula say? Whatever that angle is, this is going to be exactly half of it.
So it'll be theta divided by 2.
Kick ass. Let me stop for a minute. In fact, a little side note before I keep going. So this is not better. This is not the new thing. This is nothing. This is just going to help me in a minute. It's It's gonna help me in a minute because we currently know how to do the sine of twice an angle and the cosine of twice an angle. It's actually more useful. Tell me real quick, is there any angle that we know already that we don't know twice that angle? So give me an angle that we know the cosine of. Any angle that we know the cosine of. 270, sure. What's twice 270? 540. Couldn't I take a rotation off and that would still be an angle I know? 30. What's twice 30? 45. What's twice 45? Don't I keep getting angles I already frickin' know? What would be better is if I know an angle and I want to know half of that angle. That would be a more useful thing because that would be, all right, so give me an angle we know 30. Do I know the cosine of 15?
No.
No. Yes? Okay. So what would be better is to have a half angle formula. So that's what we're going to work on. But I want to do a little something right on the side here. So let's see. Maybe you guys could just watch this. Remind me what sine of 2 theta is.
2 sine theta plus theta.
Now, I do not blame you if you get this wrong. So feel free to just blurt it out. What is sine of 4 theta?
Sine theta, cosine theta.
So we got one vote for that.
Sine theta, cosine theta plus 2 sine theta.
So that would be the same thing. So I got 2 votes for that.
2 sine 2 theta cosine 2 theta.
So I got a vote for 2 sine 2 theta cosine 2 theta. So here's what the actual reality is. It is not 4. This 2 is not here because of this 2. It isn't. It's just a coincidence. Isn't the sine of twice 2 theta? So here's what's weird about understanding formulas. You have to understand the relationships between the input and the output. So this says, I know what the sine of twice any angle is. It is 2 sine angle cosine angle. Is this twice an angle, the way it's written? I can't use this formula then. But if I write it like this, now I have twice an angle. So this is just like Lois said. So what would sine of 6 theta be?
2 sine 3 theta cosine.
Yeah, 2 sine 3 theta cosine 3 theta. Why? Because 3 theta is what is being doubled. This is the double angle formula. I have to know what angle is being doubled in order to use it. You guys with me? I love you guys. You're all like, we're in the same room, man. You guys with me? Understanding? That is a very understandable mistake to make, so don't feel bad, Chad. It was perfect. I don't blame you at all, because that's what it looks like it should be, but it's a double angle formula, so that's what it's based on. Okay. So coming back to this. This relationship says whatever angle this is, half of it goes there. That's what that says. This is twice theta, and I put theta there. So if it was 22, I would put 11 there. If it was theta, I would put half of theta there. If it was 8 theta, what would I put here? Holy shit. Okay, so. Let me see. Let me write this again over here. I need some more room. Got it. Now I'm going to solve for this. I'm going to solve for cosine theta over 2. So in that case, I'm going to have a half angle formula for cosine. And you're all like, thank God, I was wondering how I was going to get that. Okay. So I'm going to add one that's crazy. What am I going to do now? Or what would you do if you're trying to solve for cosine?
Multiply by 2.
Divide by 2. I'm going to write it like this because I'm crazy. Now what are you going to do?
Split the 1 into cosine squared theta plus sine squared theta.
This one here?
Yeah.
So what I'm trying to do right now is I'm trying to get a formula for cosine of half an angle. So I'm trying to get cosine theta over 2 by itself.
So we do square root.
Yes, so I want to kill that square. Does that make sense? So I'm going to take a square root now. Does anybody remember when I take a square root, what do I have to put? Plus or minus. So then I get, I'm going to write this one over here. So I get cosine theta over 2. These cancel each other. Die. On this side I get plus or minus square root of 1/2 cosine theta plus 1. I'm wondering how the book puts it. Sorry, let me check. They probably write it a different way. Yeah, okay. I can write it that way, sure. You can write it like this. This might look a little bit better in a way. That's the same thing, is that cool? Those are the same, okay. So now, if I wanted to know what the cosine of 22.5 degrees was, is that half of an angle that we know?
Yes.
Because what's twice this?
45.
So this is 45 degrees divided by 2. Now, why is there a plus or minus here? Because cosine is sometimes positive, sometimes negative, depending on what quadrant we're in. What quadrant are we in?
First.
So what side do I pick? Plus. You guys, is that cool? Nothing crazy? Nothing too crazy, I should say. If I said cosine of 105 degrees, what quadrant is that? Second quadrant. I would have picked negative, because cosine is negative, because the x-axis is negative in the second quadrant, yes? And cosine likes x. You guys with me? That's the plus or minus I have to put for the square root. And how does it relate physically? Well, whatever quadrant I'm in, that's the sign I pick, based on what if cosine's positive or negative. Okay, I like it. All right, so what do I put over here? Jeff, we just had a whole discussion. So we picked the positive. What do I put inside here?
Cosine of 45.
45, good, because that's twice. What's that? Here's where you guys are going to really get excited. What's the cosine of 45 degrees?
2 over 2.
Okay. Now, if you just circle that, you're going to lose a point. Why?
Technically, there's a radical.
Because I'm an asshole. No, because,
There's a radical.
no. Is there a fraction inside of a fraction?
Yeah.
Yep. Okay, so what do I do to top and bottom to kill this fraction? Yeah, multiply by 2. So what will this become? The 2's cancel. 1 times 2 is crazy enough 2. And on the bottom I would get 4, which means I can actually write this as square root of 2 plus 2 over, what's the square root of 4? 2. Shabam! Oh my God. Remember this, what was the question? The question was the cosine of 22.5 degrees. Can you guys, Gus, take a moment and check that. Check that answer.
Yeah, can you simplify it even further by saying that it would be rad 2 over, or it'd be rad 2 plus 2, or rad, it would just be the square root of 2?
Huh?
Since the 2's would, wouldn't the 2's cancel out?
Which 2's? Sorry.
Right at the bottom right there.
This one?
Yeah,
Is it inside of a root?
no.
So it cannot interact with stuff that are inside of a root. If it was the square root of 2, I could then pull it in. But it's not the square root of 2.
Or not, sure. It wouldn't be square root of 2 2 plus 1 then?
Definitely not. Because again, this cannot break into this.
Okay.
Does that make sense? These cannot cancel. So a lot of things. These cannot cancel. Even if they could cancel, this is also being divided by this. But neither one of them can be divided by this because they don't both have the same root. You guys cool with that? So real quick side note, just because this is going to come up because there's a lot of radicals running around. What's the square root of 15 divided by 5? You ready? It's that. What's the square root of 15 divided by the square root of 5? Square root of 3. There. So why am I allowed to do this? Because they both have the same root. I got half of 15 divided by half of 5 equals half of 3 all day long. Half of 15 divided by a whole 5. Well, maybe. Whatever you say, Jeff. This math shit just keeps getting weirder and weirder. Are you guys doing okay? Now this is a little weird, yes? You don't see radicals inside of radicals too often. But the great thing is, I don't have to do anything with it. So let's see, cosine of 22.5. Am I in? Yes. I get this. So what you guys got? Oops.
Yes.
Alright, so now if I want to plug in this other thing, I'm going to put square root of the square root of 2, and then I'm going to come out of that square root plus 2. Going to come out of that square root divided by 2. Now, does anyone have the old calculator that you don't have the square root that kind of like extends? Does everybody's square root get longer like this?
How do you do that?
Huh?
How do you make do that?
You have to have the right thing. So let me see. You ready? Hit this button with me. What was it again, Jeff? Mode? Yes, mode. Do you have the math print option?
Yeah.
Oh, cool. Is it highlighted?
I have one in classic.
Yeah, classic. So let me show you. Classic mode would get out of there. Help me out.
It would give me parentheses.
Second quit.
Thank you so much. Classic mode would do this. Square root. Square root of 2. So then I have to close a parenthesis there. Plus 2. Close a parenthesis there. Do you see? I don't know if does anybody's look like this?
The double parenthesis.
Well, this parenthesis closes that square root. This parenthesis closes that square root. You see that? Divided by 2. It's just, with the math print, it's just easier. So if you hit mode and you have the math print option, that's a really good option to pick. Because then, for example, exponents go up in the exponent, stuff like that. Okay. Alright, maybe. So is it a requirement for you to be able to check this? Not really. Is it really good to be able to do it? Yeah. I'd like to know if I'm right. So you always want to have a way to check your work. Check yourself. Okay. Let's see, where am I at? Okay. So now we know the cosine, which one did I do? Cosine? Yeah, cosine of theta over 2 is plus or minus square root of 1 plus cosine theta over 2. Or did I write it the other way? I can't remember which way I wrote it. I wrote it the other way. Okay, you're fine. This is what it is. Okay. You can put cosine theta plus 1 on the top. It doesn't matter. Okay. Now I want to know what sine of theta over 2 is, and just to save you from more of the same. The way that we developed this formula was we started with this. The way I'm going to develop this formula is I would start with this fact. Cosine of theta equals 1 minus twice sine squared theta over 2. Remember that was one of the other ways to write cosine 2 theta?
Yeah.
So if I do all this, I'm going to spare you this. I've already made you suffer through one derivation. If you do all this, there's one little change that happens. This becomes 1 minus sine theta. No, it doesn't, Jeff. Cosine theta over 2. You write that again. Sine theta over 2, add sine on the brain. So here's another example where cosine's an asshole. Cosine gets the positive, sine gets the negative. That's a very minor asshole to the work. So let me give you this. Now that you're all French with me trying to write this down, let me show you how you didn't have to worry about that. Sure. Alright, so just to really explain this, hopefully it's self-explanatory. Dark black line. Roar. Everything up here you have to know. So everything up here, let me make sure, I think we covered everything. Yeah, we just did half angle. There's double angle. There's the even odd stuff. These we didn't really focus too much on, but they were in the book. The fact that sine and cosine are offset by 90 degrees, that we definitely talked about. These two are the only two that we haven't talked about yet. There we go. These are in our future. And I kind of wish I hadn't given this to you, but too bad for me. Real quick, look at that law cosines thing. Look at the last line. If I just do this, what's that? So this is what the real Pythagorean theorem looks like for any triangle, even if it's not a right triangle. So that funky ass little letter there, that's the Greek letter gamma. Come back to me. There we go. This little guy. This little guy here. That would be, tell me this, if that was 90, what's cosine of 90? Cosine 90 degrees is 0. So yeah, that would just become Pythagorean theorem if it was a 90 degree angle. So it'd be a right triangle. If it's not a right triangle, that's not 0, this thing shows up. So the Pythagorean theorem that you guys know is not the full one. It is a specific case for right triangles. If it's not a right triangle, this works. We will prove this, just in case you're worried that we won't. Yes?
So you would use the other ones if you're trying to find other angles?
This guy?
No.
No, what do you mean? Oh, these guys, it just depends on what you call A, B, and C. The minute there's not a right triangle, there's no like hypotenuse, right? So A, B, and C could be whatever you want. If you happen to call C the biggest side, then maybe that last one is what you would use. But
So are these all pretty much the same?
they're all the exact same formula, just A, B, and C interchanged, right? Notice, real quick, whatever letter's on this side doesn't show up at all on the other side except for the angle. So these angles go together. A goes with alpha, B goes with beta, C goes with gamma. But then you got BC, BC, AC, AC, AB, AB. ACDC. No, you don't have ACDC. Okay. So yes, there are two things we haven't talked about, but I just want you to have this because we're starting to get a lot of identities. So I want you to have a one-stop shop to go to for everything. Okay. So if you're doing your homework, you don't have to sit next to you, I don't quite understand you. Everything below the dark black line is an identity, but it's definitely ones that I don't care as much about, especially this guy. They are used, but nowhere near as much. So whenever I need one of these, as a math guy, I just look it up real quick. I don't have these memorized. Okay. Let me make sure I don't forget anybody. Yeah, good, okay. Perfect. Yeah, that's a little weird. Oh yeah, that's right, we don't do the law of sines and cosines until chapter 7. Yeah, okay. Any questions on this thing? You guys, anything look really weird besides those two that I said we haven't talked about? Is everybody, everything, yes?
Would we ever use the identities under the line in a different class?
Totally possible. If it's here, every single math course understands this is a departmental decision that students do not have to memorize these. So if you take a future math course and your teacher says, you're supposed to know these, talk to the chair. Talk to them first and say, I was told that was a math department said that I didn't have to know these. Right? Do you see what I'm saying? Okay. All right. These people should make you know. These up here.
Can you briefly go over the domain and range?
Yeah. So we're about to get into the inverse trig stuff. We have talked about inverse trig a little bit. So this should kind of make sense. Help me out. If I ask you what the cube root of 64 is, some of you guys might just have it memorized, but what do you have to think about to do that?
What time, and what?
You have to think backwards, don't you? Cube root, and what you just said was what times what times what, that's cubing. How do cube root and cubing something, how do they relate to each other? And what's the official name for that in math? Inverse functions. Okay, so let's talk, we're about to get into chapter 6, which is all about inverse trig. We talked a little bit about inverse trig already, if I remember correctly. But we really didn't get too in depth into it. So if you were excited about that fact, I'm sorry, we're gonna do it now. Let's see. Okay. Yeah. So let's talk about inverses in general.
This is chapter 6?
Yes.
Gotcha.
So it's not just trig functions, any inverse. So if I said my function was x minus 2, what function is the one that does the opposite of what that does? Yeah, holy shit, right? So that's what inverse means. It doesn't mean reciprocate. Sorry. That was mostly for comedic effect. Huh?
Does it mean reciprocal?
Exactly. That's what I want you to immediately understand. It does not mean reciprocal. That's why this notation that we picked, and again, the drunk history of math that I talk about sometimes they were really drunk, but this symbol normally means flip. But when I put it on a function, it means the inverse function. It means the function that does the opposite. So if my function was originally subtract 2, it's now the inverse would be add 2. That's insane.
So it's the opposite, not good.
Totes. So in general, let me see if you guys get this. If I have a function, and I know its inverse exists, if I know that g of 2 is 7, what is g inverse of 7? 2. Yeah, so the inverse, whatever g did to 2 to make it become 7, g inverse will undo all that shit and make it become 2 again. I like it. So like up here, for a concrete example, what's f of 5? What's f of 5? 3. What's f inverse of 3?
5.
Holy shit. So there are functions that undo each other. Yes? So the inverse function just does the opposite. Whatever the input is for the original is the output for the inverse. Yes? I like it. You like it? So, very quick side trek I want to go on. So I'm going to make it very, very, very basic function here. We can do this, Jeff. There, 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 there. Okay. So there's my function. There he is. He's a cute little function. So I'm going to say this is function h. And I want to graph the inverse of that. What did we just say the inverse does? Whatever the input was for the original becomes the what for the inverse?
The output.
Yes, whatever the input was for the original becomes the output for the inverse. So see how every x and y just flip. You see that? So help me out. Let's do this the real full way here. What points does h go through? Assuming this is 1 by 1 by 1.
0, -2.
Okay, sure. 0, -2.
-4, -3.
-4, -3. 1, 2,
4, 3.
4, 3. So what points will the inverse go through? -3, -4. -2, 0. 2, 1. 3, 4. So let's see what this looks like. -3, -4. -3, -4. Dang it, Jeff, you didn't go far enough down. That's all right. -2, I can't read my own writing, I love it. -2, 0. You're like, you know what we feel like, Jeff. 2, 1. And 3, 4. I should have made 3, 4, Jeff. It should be up here. There we go. Now it looks a little bit better. Yes.
So there's a kind of flip on that. I don't remember what that one y equals x.
Totally. The mirror is at y equals x, which totally makes sense because I'm switching the x and y. So the picture flips across the x and y at the x equals y line. Anybody ever heard of? Now, real quick, this is total side note to this side note. Anybody ever heard of the Nazca lines down in Peru? People made. You have?
Yeah.
Yeah. How do you know about them?
I'm Peruvian.
There you go. What part? Or did you live there?
Well, my mom's from Peruvian, from Lima.
Oh yeah. Okay. Like in 2010, I went down there because I was dating somebody who was Peruvian. We went down and stayed with her mom. Went to Cusco, went to Machu Picchu, all that kind of stuff. Yeah, it was crazy. Oh my god. He's cool. That's yummy. Okay. So Nazca lines are just these lines that ancient people made, but you can't see what they actually draw unless you're way the hell up in the air. So there's all these theories about maybe they had hot air balloon technology, maybe it was aliens, right? You see that on the Learning Channel, whatever the thing is with the guy.
History Channel.
Yeah, the History Channel. So you know what I'm talking about. They're aliens. Sorry. If you don't know what I'm talking about, it's probably better. Okay. Now, all of this is not trig, I understand, but we're about to talk about inverse trig functions. We have to remember what inverse functions are. So this is what they fundamentally do. Do you all agree with me the original thing I drew was a function? What's the test to see if something's a function? Vertical line test. So does the original function pass the vertical line test? Check. Every vertical line I draw only goes through it once. Only once. At least once. No. Exactly once. For the purple line, does it also pass the vertical line test?
Yes.
Yes. Good. Now, so therefore, an inverse function existed for the function I drew. Would an inverse function exist for a parabola? If I flip it over the y equals x line, is that a function?
No.
It does not pass the vertical line test. So there is no inverse function for this. But what? Now listen. Some of you guys may be saying, but Jeff, if I have something squared, how do you kill the square? You take a square root. Does anyone know what a square root function looks like? as a graph.
Not yet.
Oh, isn't that like half?
What's the square root of 0?
Zero.
It's the square root of 1.
Square root.
Oh,
Square root of 1.
This, right?
So square root of 1.
Square root of
What do you multiply by itself to get 1?
No, one.
Okay, what's the square root of 4? 2. Doesn't it look like a parabola that lost half of itself? Oh, right?
Yeah.
So, instead of flipping it and then doing a vertical line test, let me just flip the test. So if I do a horizontal line test and it goes through more than once, it does not have an inverse. But you might say, I know the square root kills the square, Jeff. Come on, math boy, what the shit's wrong with you? But in order for this to exist, why does the picture look like this? Why did it lose the other half of itself? Because we have to kill this side. If I kill that side, is that passing the horizontal line test now?
Yeah.
Does it only go, every horizontal line goes through once?
Yeah.
And if I flip it, doesn't it become this?
Yeah.
Hey, there you go. That explains why a square root looks like a parabola that lost its bottom half, right? It either had a rough night or a really good night. It just dropped out. Okay. Maybe. So, armed with this knowledge, can you guys, and if you can't, that's very bad. Squid, yes. I haven't told you what to do yet.
Sorry, is that what you showed above, is that you can't find the square root of a negative number?
That's part of the reason why it becomes imaginary, right? Can't be real, it can't exist on this. Yes. Can you just give me a rough sketch of sine? Going forward and backward. Rough sketch of sine. So what sine do? Where's sine start? Here in the middle.
0, 0.
0, good. And then it goes
1.
up, down, down, up. So back here it's going to go down, up, down. Is that cool? So it goes like this. Now, does that pass the horizontal line test? It
Yes.
desperately fails. If I drew a horizontal line through the sine function, how many times would it hit the sine function? Infinite number. I love it, because these humps keep going forever. Yes?
But it does pass the vertical line test though.
I was waiting for that song to happen, but yes. Say it.
But it does pass the vertical line test though.
Totally, it's a function. Yes, a sine function is a function. But is it invertible? Can I find the inverse function? Not the way it is. So what am I going to do? I'm going to do the same thing we had to do up here. I'm going to erase part of it. I'm going to restrict the domain. Yes?
Why do we need the horizontal line test? Can't we just use the...
Vertical tells me if it's a function. I already know sine is a function. Horizontal tells me if it's an inverse, if it's invertible, if an inverse exists. And again, just to remind you guys, if I did flip this and then apply the vertical line test, I'm like, oh, the inverse wouldn't be a function, so I don't have to worry. So what do I do instead? I flip the test. I just do a horizontal line test. Instead of flipping the function and then applying this, I just freaking apply this. One step. So that's why the horizontal line test exists. It is a vertical line test that I flipped. So, do you guys see this is not, doesn't pass a horizontal line? For example, right here, it starts to turn on itself, and that would not pass a horizontal line test, yes? So do you agree that if I just chop it right there, that's better so far? Now where does it start doing the same thing to itself back here? Right here, yes?
Yeah.
So I just chop it right there. So if I make the domain, what's this and what's this? No, come on, you're better than this.
Negative pi over 2.
When a sign hit 1,
Pi over 2.
pi over 2. And the sign hits negative 1, if we go back pi over 2. Is that cool?
Yeah.
So the domain would be negative pi over 2 to pi over 2. If I do that, then an inverse function exists. Because now this piece in the middle passes the horizontal line test. So, dear God, Jeff, just tell me in plain English what the hell that means to me. Here's what it means. Remind me, what does inverse functions do? They take the x and y of the original and they just flip it, right? Remind me, what's domain? It's a collection of all the what?
X values.
X values. What's the range?
Y
Y values.
Y values.
So if the function has a domain of this, the inverse function is going to have a range of this. The domain and range just flip. What quadrants is this in?
First and fourth.
First and fourth, kick ass. So if I know my angle is supposed to be in the third quadrant and I do an inverse sine, it can never give me the angle that's in the third quadrant. It's forced to live between negative pi over 2 and pi over 2. Why is it forced to live between there? Because the only way to make it exist in the first place was to restrict the domain. Poor little dude. It's not the inverse sine's fault. So, let's do this. Help me out, guys. What is the sine of sine of 150 degrees? Kind of gave the game away a little bit.
1/2.
Say again?
1/2.
Yeah, 1/2. You guys with me? You all have a calculator now, right?
Yeah.
Do you guys see where your inverse sine function is? Conveniently right above the sine button. That's silly. If I do inverse sine of 1/2, I'm not going to get 150 degrees. Let me first make sure everybody's in degrees. Let's all make sure we're in the same boat.
Yeah.
So everybody in degrees. Hit the mode button, make sure you're in degrees. Okay. So let's all do this together. Let's do inverse sine of 1/2. Yes. So sometimes when I do inverse sine, poor little inverse sine, it can only give me numbers that are between negative 90 and 90, negative pi over 2 and pi over 2. If I know my answer is supposed to be in some other quadrant, the answer it gives me is actually a reference angle. Become a 3. So what if, let's do this, what if I had this angle? What angle is that? That's going to be
210.
210. What's the sine of 210? Almost.
-1.
Negative 1/2. But if I do inverse sine, let's try to do inverse sine of negative 1/2. Try to do that. Shit and a half. It's inverse sine of negative 1/2. We get negative 30. Is that the answer I want?
No.
Again, now it's negative, which is a little weird, but it's the best the poor little inverse sine can do for me. It's saying I'm actually going back like that way 30 degrees. So I'm in the third quadrant. So the output for an inverse sine or any inverse trig is going to be at worst a reference angle. It's not going to be the actual angle I want sometimes. I'm the human. I need to know which quadrant I'm supposed to be in. Yes?
If you put negative 150, like, to find the angle instead of 210, would that be wrong?
No. Yeah, it's the same angle. Yeah. You'll get the same thing, of course, right? Sine of negative 150. Yeah. Okay. So that's one little thing about inverse trig that's a little weird. How do I do
You all see what inverse trig functions do we have?
Sine, cosine, and tangent.
Now, let's talk about this. So let me ask you a couple questions here. What's the inverse sine of, you can do it, Jeff, rad 2 over 2.
45.
You don't have to do this in a calculator. In fact, do not do this in a calculator. It's already done for you. 45. What if I want it in radians?
5 over 4.
Okay, cool. I like it. Can you put into your calculator the inverse tangent of 1.7? So this one, you should not use a calculator for. This one, you're going to need some help. We don't have 1.7 output memorized for tangent. So where's inverse tangent? Crazily enough, it's next to tangent. So inverse tangent of 1.7. Well, you got 59.5 degrees roughly. So no big deal, right? No big deal? So do inverse secant of 3 over, no, Jeff, try it. Do inverse secant of 11 over 3. Do you have an inverse secant button?
No.
No.
You do 1 over inverse. Doesn't work.
So let's talk about it. You ready? So what is the output to an inverse trig function? Oh shit. What's the input for any trig function? Geometrically, what is it? An angle. Take X. This morning in my pre-calc class, it took 5 minutes. So the input for a trig is an angle. So what's the output to an inverse trig?
An angle.
An angle. Take X. I love it. Ooh, all right, now watch. This is where things get nifty. I'm going to analyze this a few different ways. I am going to tell you how to put this in the calculator eventually, but I want to look at it by hand first because it's just the kind of guy I am. Now watch this. Real quick, side note, don't even write this. If I wanted to solve this equation, what would I do? Take a cube root of both sides, because those are inverses, they will kill each other, and then that shit I can throw on the calculator. You guys with me? Yeah. Okay. How do I solve this? How do I, not really solve it, but how do I kill this? How do I get 11/3 kind of by itself? How do I get rid of this?
By cosine. Or-
Two things. Cosine's not going to touch that, because it's not inverse cosine. It's inverse secant. Second thing is I'm not multiplying by a damn thing. Did I multiply both sides by a cube root? Do you see how this, isn't that weird to say? I took the cube root of both sides. Here, yes? Okay. So what do I do to kill an inverse secant? I take the, what's the inverse of inverse secant? Secant. Take the secant of both sides. What do these two things do? They do their jobs, they die, right? Sorry, that's so morbid. This is how you guys knew what the answer was up here. When I say inverse sine of rad 2 over 2, you're saying to yourself, what do I take the sine of to get rad 2 over 2? Because inverse functions are backwards. You've got to think backwards. So sine of 45 is rad 2 over 2, therefore inverse sine of rad 2 over 2 equals 45. So I already know that this statement says, what do I take the secant of to get 11 over 3? So I really just rewrote it to capture that idea. Can you draw the triangle that this lives in? Every trig function value, I can draw a triangle it represents. Which side is 11? Which side is 3?
11 is R. And then
Secant's related to cosine, so which side is 3?
X.
The x side. You guys with me so far? Okay. So that is what an inverse trig function by itself really represents, is a right triangle, and you know what two of the sides are. I like it. Now, what is what is the secant of theta here? This is going to be silly for a second, but that's all right. We already know this. What's the secant of theta?
11 over 3.
Holy shit. What is the cosine of theta?
3 over 11.
So wouldn't this mean that theta is the inverse secant of 11 over 3?
Yeah.
What does this one say? Theta is the inverse cosine of...
3 over 11.
Ah, so I don't do, to figure out secant, I don't do 1 over inverse cosine. I do inverse cosine of the reciprocal on the inside. Why did I have to go through all that? Because do you have an inverse secant button on your calculator? You don't even have a secant button on your calculator. But I want you to be careful. You don't just do 1 divided by inverse. No. If I want to figure out, if my question is, what is the inverse secant of 11 over 3, and I do not have an secant button, I just put in here the inverse cosine of 3 divided by 11. That's what I flip. Because that would be the flipping of the sides. Yes? That is not immediately obvious that that's what I would do. But that's what I would do. So can you guys, so we got that to be 74.2 roughly. Agrees. Can you please figure out for me what the inverse cotangent of 3 is? So it'll be the inverse tangent of what?
1/3.
There you go. So then you just throw that in a little calculator. You get 18.43 roughly. Is that cool? Or is that understood, I should say? It's probably not quite cool, but. Alright, that's plenty for today, guys. So we finished chapter 5, and we are into chapter 6, if I remember correctly. It's really weird teaching the same topics in 2 different classes. Yes, we finished chapter 5, and we just got into chapter 6 a little bit.
So you see you're teaching a pre-calc class this semester?
Yes.
Are they gonna operate in further semesters as well? I heard that they might be getting rid of.
Oh God, dude. I have so many rants inside of me. Do y'all know, real quick, I can't remember if I talked about this. Do y'all know that it's illegal for us to teach intermediate algebra, Math 110? We used to have a class called Math 110, which is like Algebra 2, just a little bit beefier, to get people ready for the pre-calc and so forth. It's illegal for us to teach it now. AB 705 and AB 1705, 2 bills that basically said, stop doing that stuff, you evil math people. And so now we're trying to get a bunch of student experiences together to show why we need it. They should have the option. Students should have the option to take it if they know that they need it. Would you agree with me or not?
Yes.
Now I agree that our placement processes needed to change, and we've been trying to work with the state to help us change them. And all of a sudden they said, no, instead of changing the placement process, we're just not going to let you teach those classes. So what Chad's talking about is they're going to do the same thing to pre-calculus, or they're trying to.
I heard about that.
And there are a lot more people that are kind of at least iffy, if not outright against that. The unfortunate thing for math teachers is they don't listen to us because we're biased and we're evil and we just want to torture students. So whatever we say is really quickly just, whatever. So that's why I tried to talk to the student governments in here, and they put together a task force, and they got together with the state student senate, and they try to push back, because if we get enough students that say this is hurting us, maybe the state will actually change back a bit, right? Sorry, that was all side note, but just because it came up, yeah.
Is pre-calc the trig in college algebra?
Pre-calc is like 170 and 175 put together.
So
Just
we do
need
175 instead.
Yeah, so.
Yeah, if you take 170 and 175, it's equivalent to 176. But 175 is on the chopping block too. It's the same thing. Right? So they're basically saying any STEM student will have to start in calculus in community college. Anyway, that's enough. Okay, guys, that's enough.
Which is ridiculous, my high school was not allowed that calculus. Like,